Prisma sdwan Policy Framework Overview. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this series we are going extremely deep into the Prisma sdwan Policy Configuration Framework. If you have already watched the introduction series, you understand the high-level architecture. Now we are going to go inside the policy engine, the brain of the entire sdwan system, and understand exactly how every policy type works, how they interact with each other, and how to configure them correctly for production deployments. Prisma sdwan policies are not a single monolithic configuration block. They are a collection of distinct, layered policy types that each control a different dimension of how traffic is handled. The 5 major policy types you need to master are: network policy, which controls path selection and WAN transport assignment; application policy, which defines per application SLA requirements and routing preferences; security policy, which controls what traffic is permitted between zones; QoS policy, which governs bandwidth allocation and queue prioritization; and NAT policy, which handles network address translation for both inbound and outbound traffic. Understanding how these 5 policy types stack on top of each other and in what order they are evaluated is the foundation of advanced Prisma sdwan knowledge. An interviewer will often ask you to walk through what happens when a packet arrives at an ION device. If you can describe the policy evaluation sequence accurately and completely, you demonstrate expert-level understanding. The diagram on this slide shows the policy evaluation stack, the order in which policies are applied to a flow as it enters and exits the ION device. We will spend the rest of this series unpacking each layer in detail. Application policy. For app SLA and routing. Application policy is the most distinctive and important policy type in Prisma sdwan, and it is what fundamentally separates this platform from traditional routing. While network policy controls which path traffic takes, application policy controls the quality requirements that path must meet for specific applications and sign triggers automatic rerouting if those requirements are violated. Let me take you through every component. The first building block is the application group. Rather than writing individual policy rules for every single application, which would result in an unmanageable number of rules, Prisma sdwan allows you to group applications with similar characteristics into application groups. For example, you might create an application group called UC Apps containing Microsoft Teams, WebEx, Zoom, and any other unified communications applications. You would create another group called Critical SASE containing Salesforce, ServiceNow, and Workday. You would create a third group called Bulk Transfer containing FTP, SFTP, backup software, and Windows Update. Application groups are maintained centrally and referenced by application policy rules, so adding a new application to an existing group automatically applies all existing policies to it without requiring policy rule changes. The second building block is the SLA profile. An SLA profile is a named object that defines the maximum acceptable network performance thresholds for a specific traffic class. An SLA profile has 4 configurable parameters: maximum one-way latency in milliseconds, maximum jitter in milliseconds, maximum packet loss as a percentage, and the minimum bandwidth guarantee. The ION device evaluates every available WAN path against the SLA profile for each active flow and selects the path that meets the SLA thresholds while also satisfying the path preference defined in the network policy. The third building block is the application policy rule itself. Each rule specifies which application group it applies to, which SLA profile must be satisfied, the preferred path ordering if multiple paths meet the SLA, whether FEC or packet replication should be activated when path quality degrades, and what action to take if no path can satisfy the SLA, either fall back to the best available path or drop the traffic entirely. This last option, dropping traffic when no SLA compliant path is available, is used in strict compliance environments where sending over a degraded path is worse than temporarily failing the connection. QoS policy. Queue profiles and bandwidth control. Quality of service policy in Prisma sdwan controls how bandwidth is allocated across competing traffic flows and determines the priority in which different application classes are serviced when a WAN link becomes congested. Mastering the quality of service policy model requires understanding both the queuing architecture and the bandwidth management mechanisms. Let me walk through both in detail. Prisma sdwan uses a hierarchical token bucket queuing model. Each WAN interface has a configurable bandwidth contract. This is the rate you configure to match the actual circuit capacity of the WAN link. It is critically important to configure this accurately, because the QoS engine uses this value to determine when the link is congested and when to start enforcing queue priorities. If you configure a bandwidth contract that is higher than the actual circuit capacity, the QoS engine will not start prioritizing traffic until the link is already overloaded, defeating the purpose of QoS. If you configure it too low, you will artificially restrict traffic below the available capacity. Within the bandwidth contract, traffic is distributed across queue profiles. A queue profile defines a traffic class with three key parameters. The first is the bandwidth percentage, the guaranteed minimum share of the total WAN bandwidth allocated to this queue. For example, a real-time queue might be configured with a guaranteed 30% of bandwidth to ensure voice and video always have capacity. The second parameter is the burst percentage, the maximum bandwidth this queue can consume when higher priority queues are not fully utilizing their allocation. The third parameter is the scheduling weight, which determines the relative priority of the queue compared to other queues during periods of contention. The four standard queue tiers in Prisma sdwan are Q0, which is real-time, used for voice, video conferencing, and latency-sensitive applications. This queue uses strict priority scheduling, meaning it is always served before any other queue as long as it has traffic waiting. Q1, which is business critical, used for ERP, authentication, and mission-critical software as a service applications. Q2, which is standard, used for general business web browsing, email, and productivity applications. And Q3, which is bulk, used for backup, software updates, and file transfers that can tolerate high latency and variable throughput. The quality of service policy rules map application groups to queue profiles using the same application identification provided by the DPI engine. This is the critical integration point between quality of service policy and application policy. Both rely on the DPI engine to correctly identify applications, and if a new application is not recognized by the DPI engine, it will be placed in the default queue, which is typically the standard tier. Policy sets and site templates. Policy sets and site templates are the configuration management mechanisms that allow Prisma sdwan administrators to apply consistent policies across hundreds or thousands of sites without individually configuring each device. Mastering these concepts is essential for anyone who will be responsible for operating a large-scale sdwan deployment, and interviewers in enterprise-focused roles will almost certainly ask about them. A policy set in Prisma sdwan is a named collection of all the policy types we have discussed: network policy, application policy, security policy, quality of service policy, and NAT policy, bundled together into a single assignable unit. Think of a policy set as a complete policy profile for a specific type of site. You might create a policy set called Standard Branch for typical retail or office locations, another called Large Campus for headquarters and large regional offices with more complex routing requirements, and a third called IoT Site for manufacturing plants or facilities with operational technology networks requiring strict segmentation. When a policy set is assigned to a site in the Prisma sdwan portal, all ION devices at that site receive and apply all the policies contained in that policy set. This means that a single policy change made to the policy set, for example, adding a new application to a quality of service queue or modifying an SLA threshold, is automatically propagated to every site assigned to that policy set. In a deployment with 500 branch sites, a single policy update in the portal can be applied to all 500 ION devices within minutes. This is fundamentally different from traditional network management where you would need to log into each device individually to make the same change. Site templates take the standardization concept further. A site template defines not just the policies but also the interface configuration, VLAN layout, DHCP scope definitions, BGP neighbor settings, and HA configuration for a specific site type. When a new ION device is zero-touch provisioned, it can be automatically assigned a site template, which configures not just the policies but the complete device configuration without any manual steps. This is the mechanism that makes mass deployments at scale feasible. Every new branch gets a complete, validated configuration from the moment it comes online. Prefix filters and traffic match conditions. Prefix filters are one of the most powerful and flexible traffic matching tools in the Prisma sdwan policy framework. They allow you to define precise traffic match conditions based on source and destination IP prefixes or groups of prefixes and use those conditions in network policy, security policy, and NAT policy rules. Understanding prefix filters deeply is a strong signal of hands-on configuration experience. A prefix filter in Prisma sdwan is a named list of IP prefixes, either individual host addresses, subnets, or aggregated ranges. For example, you might create a prefix filter called RFC 1918 private that contains RFC 1918, representing all private address space. You might create another called Office 365 endpoints that contains all the Microsoft 365 IP address ranges published by Microsoft. Prefix filters are maintained as reusable objects that can be referenced by multiple policy rules, so when Microsoft updates its IP address ranges, you only need to update the prefix filter once, and all policy rules referencing it are automatically updated. In network policy, prefix filters are used as destination match conditions. A common use case is creating a rule that says all traffic destined for Microsoft 365 IP addresses, matched by the O365 endpoints prefix filter, should be sent directly to the Internet via the broadband path, bypassing the MPLS circuit and the data center. This is called a direct Internet access or local Internet breakout rule, and it is one of the most impactful configurations for improving Microsoft 365 performance in branch offices. Without this rule, Microsoft 365 traffic would hairpin through the data center, adding unnecessary round-trip latency and consuming expensive MPLS bandwidth. In security policy, prefix filters are used as source or destination address match conditions in rules. For example, a rule permitting the Internet of Things zone to communicate with a specific management server in the data center would reference a prefix filter containing only the management server's IP address as the destination match, ensuring that Internet of Things devices cannot reach any other internal resource even if they are somehow compromised. In NAT policy, prefix filters are used to define NAT exemption rules, the no-NAT rules we discussed earlier. The prefix filter containing all internal corporate subnets is referenced in the NAT exemption rule to ensure that traffic destined for any internal address is never subjected to source NAT. Maintaining an accurate and up-to-date prefix filter for internal corporate address space is an operational responsibility that is often overlooked when a new subnet is added to the corporate network without updating this filter. Traffic to that subnet gets NATed and connectivity breaks. Service binding and WAN interface labels. Service binding and WAN interface labels are configuration concepts that control how the Prisma sdwan controller understands and categorizes the WAN interfaces on each ION device, and how policies reference those interfaces in a transport-agnostic way. These concepts are fundamental to writing portable, scalable policy configurations that work correctly across sites with different WAN transport combinations. A WAN interface label is a tag applied to a WAN interface on an ION device that describes the characteristics of that interface, specifically its transport type and its intended role. Standard WAN interface labels include private WAN for MPLS circuits, public WAN for broadband internet connections, and LTE for cellular backup connections. You can also create custom labels for non-standard transport types. The label is assigned in the ION device configuration for each WAN interface, and it is this label, not the interface name or IP address, that policy rules reference when specifying path preferences. This abstraction is what makes Prisma sdwan policies portable. Imagine you write a network policy rule that says real-time application traffic should prefer private WAN paths and fall back to public WAN paths. This exact same policy rule works correctly at a branch with a single MPLS circuit and a single broadband connection, at a branch with two MPLS circuits from different carriers both labeled private WAN, and at a branch with only broadband connections where private WAN is unavailable. In the last case, the rule automatically falls back to the public WAN path. The policy never needs to reference specific interface names or IP addresses, which would break when interfaces change. Service binding is a related concept that associates a policy set with a set of service endpoint definitions that are specific to the sites using that policy set. A service binding tells the sdwan system which cloud security gateways, which data center endpoints, and which internet breakout preferences apply to sites in a specific geographic region or deployment tier. For example, a service binding for European sites might point to Prisma Access compute nodes in Amsterdam and Frankfurt as the preferred security gateways, while a service binding for North American sites points to nodes in New York and Los Angeles. The same application policy and network policy rules apply to both regions, only the service binding differs, ensuring that traffic is always directed to the geographically nearest security enforcement point. Advanced path steering, conditional and priority-based rules. Advanced path steering in Prisma sdwan goes beyond simple preferred path and fallback path configurations. In production enterprise deployments, you frequently need path selection logic that reacts dynamically to real-time conditions, combines multiple match criteria, and handles edge cases gracefully. Let me walk you through the advanced path steering mechanisms in detail. The first advanced concept is conditional path steering based on real-time SLA compliance rather than static path preference. In a basic network policy rule, you specify a preferred path group and a fallback path group. The device will use the preferred path unless it is completely down. But in advanced configurations, you combine network policy with application policy SLA profiles so that the path selection engine switches away from the preferred path not just on failure, but whenever the SLA metrics latency, jitter, or loss degrade below the threshold defined for that application class. This is called proactive path steering, and it is one of the key differentiators of Prisma sdwan versus products that only fail over on complete link failure. The second advanced concept is multi-criteria traffic matching in network policy rules. A single network policy rule can match on a combination of conditions simultaneously. Source security zone, destination prefix filter, application identity from the DPI engine, DSCP marking on the incoming packet, and time of day schedule. Combining these match criteria allows you to write precise rules like traffic from the finance zone destined for the payment processing prefix, classified as SAP application, during business hours, should use MPLS exclusively with no internet fallback. The same traffic outside business hours can fall back to broadband, because the finance team is not working and the data is lower priority. This level of policy granularity is impossible in traditional routing architectures. The third advanced concept is asymmetric path steering, which handles the case where inbound and outbound traffic for the same application should take different paths. For example, a video surveillance application might upload large volumes of video data outbound on the broadband link to save MPLS bandwidth, while the management traffic for the camera system takes the MPLS path for reliability. Prisma sdwan handles asymmetric steering through session-aware policy evaluation. The outbound flow classification determines the path for both directions of that session. Policy debugging and troubleshooting workflows. Policy debugging is where theoretical knowledge meets practical skill. and it is a topic that consistently separates candidates with genuine hands-on experience from those who have only studied documentation. In a Prisma sdwan environment, policy misconfigurations are the most common cause of connectivity issues and application performance problems. Knowing the systematic debugging workflow and the specific tools to use at each step is essential for any operational role. The first and most important debugging tool for policy issues is the flow monitor in the Prisma sdwan portal. The flow monitor shows every active and recently completed flow through a specific ion device, with detailed information about how each flow was processed through the policy pipeline. For each flow, the flow monitor shows which application was identified by the DPI engine, which security policy rule permitted the flow, which application policy SLA profile was applied, which way-in path was selected by the network policy, which QoS the flow was placed in, and whether the flow is meeting its SLA thresholds in real time. When a user reports that a specific application is not working or is performing poorly, the flow monitor is always the first place to look. The second debugging approach is policy simulation, also called policy lookup. In the Prisma sdwan portal, you can input hypothetical traffic parameters: source zone, source IP, destination port, and application, and the portal will simulate the policy evaluation pipeline and show you exactly which rule would match in each policy stack. This is invaluable for validating policy changes before pushing them to production and for understanding why a specific traffic type is being handled unexpectedly. If you expect a flow to match Rule 3 of the security policy but it is actually matching Rule 7, the policy simulation will show you why, usually because a more general rule higher in the stack is catching the traffic before it reaches the intended rule. The third debugging approach uses the ion device CLI for low-level inspection. When the portal-based tools do not provide enough detail, you can SSH to the ion device CLI and use commands to inspect the active session table, the overlay routing table, the BGP neighbor state, and run live packet captures. A packet capture filtered on a specific source or destination IP will show you whether the traffic is arriving at the ion device, whether it is being forwarded to the WAEN tunnel, and whether the return traffic is arriving correctly. The absence of return traffic in the capture is often the key indicator of a NAT exemption misconfiguration or a security policy deny rule blocking the return flow. Policy configuration via REST API, automation deep dive. Configuring Prisma sdwan policies through the REST API rather than through the portal is a capability that enterprise organizations increasingly require as they adopt net DevOps practices, applying software development methodologies like version control, automated testing, and continuous deployment to network configuration. Let me walk through the API-based policy configuration workflow in detail, covering the specific API endpoints and data structures you need to understand. Every policy object in Prisma sdwan, application groups, SLA profiles, prefix filters, network policy stacks, security policy stacks, quality of service profiles, NAT policies, and policy sets, has a corresponding REST API resource with a unique URI path and a JSON schema. To create a new SLA profile via the API, you send an HTTP POST request to the SLA profiles endpoint with a JSON body containing the profile name, the maximum latency value in milliseconds, the maximum jitter value in milliseconds, and the maximum packet loss percentage. The API returns a response containing the newly created object with its system-assigned unique identifier, a UUID, which you must capture and use in subsequent API calls that reference this SLA profile. This dependency chain where one API object references another by its UUID means that API-based policy configuration must be performed in a specific order. You cannot create an application policy rule that references an application group and an SLA profile before both the application group and the SLA profile have been created and their UUIDs captured. In a Python automation script, this means managing a dictionary of object names to UUIDs that is built up progressively as each object is created. The CloudGenix SDK Python library handles some of this complexity by providing methods that accept object names rather than UUIDs and automatically resolve the names to UUIDs internally. Idempotency is a critical concept for a PI-based network configuration. An idempotent operation produces the same result whether it is executed once or multiple times. When building automation scripts for policy configuration, all create operations should be written to first check whether the object already exists using a GET request and only proceed with a POST to create it if it does not exist, or a PUT to update it if the existing configuration differs from the desired state. This pattern ensures that running the automation script multiple times does not create duplicate objects or generate errors. This approach is sometimes called desired state configuration, and it is the foundation of tools like Terraform and Ansible. Policy versioning and change management. Policy versioning and change management are operational discipline topics that are increasingly important in enterprise Prisma sdwan deployments. As networks grow and policies become more complex, the ability to track policy changes, understand what changed and why, roll back to a previous known good state, and enforce a change approval process becomes critical for maintaining network stability. Prisma sdwan maintains an audit log of all configuration changes made through the portal, the API, or the CLI. Each audit log entry records the timestamp of the change, the identity of the administrator who made the change, the specific object that was modified, the previous value of the changed attribute, and the new value. This audit trail is invaluable for post-incident analysis when a network outage or performance degradation occurs. The first question is always whether a configuration change preceded the incident. The audit log allows you to correlate the timeline of events with the timeline of configuration changes. For compliance frameworks like SOC 2, PCI-DSS, and ISO 27001, having a complete, tamper-evident audit log of all network configuration changes is a mandatory control. Configuration snapshots, also called configuration backups, are a related mechanism that captures the complete current configuration of all policy objects at a point in time. In Prisma sdwan, configuration snapshots can be taken manually through the portal or automatically on a scheduled basis. A snapshot captures all policy stacks, all referenced objects, all device configurations, and all site assignments in a single exportable bundle. If a series of policy changes causes unexpected behavior, you can restore the previous snapshot to return to the known good state without manually reverting each individual change. The time to restore from a snapshot is typically minutes, compared to potentially hours of manual troubleshooting and reversion. For organizations that want to integrate Prisma sdwan policy management with a formal change management process, the REST API provides the mechanism to implement a GitOps workflow. All policy configurations are stored as JSON files in a Git repository. Changes go through a pull request process with peer review. Approved changes are merged to the main branch and automatically deployed to the Prisma sdwan controller through a CI/CD pipeline. If a deployed change causes issues, the pipeline can automatically roll back to the previous commit. This approach brings the same rigorous change control practices used in software development to network policy management. Policy for Unified Communications (UC) Traffic Optimization. Unified Communications traffic voice calls, video conferencing, and real-time collaboration applications is the most demanding category of traffic from a network policy perspective. UC applications are uniquely sensitive to latency, jitter, and packet loss in ways that other applications are not, and they require a comprehensive, multi-layered policy approach that spans application policy, quality of service policy, network policy, and sometimes forward error correction configuration simultaneously. Let me walk through the complete UC policy design in detail. The foundation of UC policy is the application group. You should create a UC Apps application group that includes every unified communications application used in your organization. Microsoft Teams, Zoom, Cisco WebEx, RingCentral, Avaya, Genesys, and any other real-time communication platform. The DPI engine identifies these applications by their traffic signatures. For Microsoft Teams, this includes recognition of the Teams media UDP flows, Teams signaling over HTTPS, and Teams desktop sharing streams. Including all UC applications in a single group allows you to apply a consistent, stringent SLA profile to all of them with a single policy rule. The UC SLA profile should be configured with the most aggressive thresholds in your deployment. The ITU-TG.114 standard defines the recommended maximum one-way delay for voice as 150 milliseconds. For jitter, the practical limit for comfortable voice quality is 30 milliseconds. Above this, audio quality becomes noticeably degraded. Packet loss must be kept below 1% for acceptable voice quality, and below 0.5% for high-definition video conferencing. These are your SLA profile thresholds. Any way and path that cannot consistently meet these thresholds should not be used for UC traffic. This is enforced automatically by the Application Policy SLA Enforcement Engine. The quality of service configuration for UC traffic must use Q0, the strict priority queue, with a guaranteed bandwidth allocation sized to support the maximum number of simultaneous calls your organization requires. A standard voice call requires approximately 100 kilobits per second in each direction. A video conference call requires 500 kilobits per second to 2 megabits per second depending on resolution. If a branch can support a maximum of 10 simultaneous video calls, the real-time queue bandwidth guarantee should be at least 20 megabits per second, 10 calls multiplied by 2 megabits per second in each direction. Undersizing the real-time queue guarantee means that during peak usage, some UC flows will compete for bandwidth in the lower priority queues, resulting in exactly the degradation you designed the policy to prevent. Finally, forward error correction should be configured for unified communications traffic with a trigger threshold below the SLA profile's packet loss limit. If your SLA profile allows a maximum of 1% packet loss, configure forward error correction to activate when the measured path loss exceeds 0.5%. This provides a margin of protection. Forward error correction compensates for packet loss before it reaches the level that would trigger a path migration, maintaining call quality during brief periods of carrier degradation without the disruption of a mid-call path switch. Policy interview questions, advanced level. This final slide in the series covers the most challenging policy-specific interview questions you are likely to encounter in a senior Prisma sdwan technical interview. These questions go beyond definition-level knowledge and require you to reason through scenarios, identify problems, and propose solutions, exactly the kind of thinking that distinguishes expert candidates. Let me walk through each question and the key points your answer must cover. The first advanced question is: a branch user reports that their Microsoft Teams calls are dropping every afternoon between 2 p.m. and 4 p.m., but the issue resolves itself by 5 p.m. How would you investigate and resolve this? A strong answer follows this structure. First, you check the path quality monitor for the affected site and look at the MPLS and broadband path metrics specifically during the 2 p.m. to 4 p.m. window over the past several days. You are looking for a pattern of latency spikes, jitter increases, or packet loss that correlates with the complaint window. Second, you check the flow monitor to confirm that Teams traffic is being correctly identified by DPI as Microsoft Teams and is being assigned to the UCSLA profile and the real-time quality of service queue. If Teams is being misclassified, it may be getting lower priority during peak hours. Third, if path degradation is confirmed on the MPLS link, you check whether the broadband fallback path is healthy and whether the SLA-based path steering is configured to migrate Teams traffic when MPLS degrades. Fourth, you review the quality of service configuration to verify that the real-time queue bandwidth guarantee is sufficient for the number of simultaneous calls during peak afternoon hours. Fifth, you consider enabling forward error correction for the Teams application during the affected time window as a temporary mitigation while the carrier investigates the MPLS degradation. The second advanced question is: you have two MPLS circuits from different carriers at a large branch. How would you configure the network policy to load balance traffic across both circuits for standard applications while keeping UC traffic exclusively on the lower latency circuit? The answer involves creating two separate path groups, MPLS carrier A and MPLS carrier B, and an MPLS any group containing both. The UC application policy rule references an SLA profile that, combined with real-time path monitoring, automatically selects the lower latency MPLS path. The standard application network policy rule references the MPLS any path group with load distribution enabled. Prisma sdwan will distribute flows across both MPLS circuits based on available capacity. If one MPLS circuit fails, all traffic automatically consolidates on the surviving circuit. This answer demonstrates knowledge of both path group design and the interaction between application policy SLA enforcement and network policy path selection. Spoke-to-spoke policy design. Spoke-to-spoke communication, also called branch-to-branch traffic, requires careful policy design in Prisma sdwan because it involves multiple policy layers working together across two ion devices and the controller. Many network engineers understand hub and spoke policy design intuitively because it mirrors traditional MPLS topologies, but spoke-to-spoke design introduces unique considerations that are frequently tested in interviews. The first question in any spoke-to-spoke policy design is whether the traffic should flow through a hub or use a direct on-demand tunnel. In a hub and spoke topology, all branch-to-branch traffic routes through the hub ion device, typically at the data center or a regional aggregation site. This design simplifies security enforcement because the hub acts as a centralized inspection point, but it adds latency proportional to the geographic distance between the spokes and the hub. For two branch offices in the same city communicating through a data center in a different city, the latency penalty can be significant. In a full mesh or partial mesh topology, Prisma sdwan establishes on-demand direct tunnels between spoke ion devices when branch-to-branch communication is needed. The on-demand tunnel is negotiated through the controller. Spoke A signals to the controller that it needs to reach spoke B. The controller validates the policy permits this communication and provides spoke A with the tunnel endpoint information for spoke B, and the two ion devices establish a direct encrypted tunnel. This direct tunnel eliminates hub latency but means that branch-to-branch traffic does not pass through a centralized security inspection point. The policy design decision for spoke-to-spoke traffic therefore comes down to a security versus performance trade-off. For latency-sensitive applications like branch-to-branch voice calls or real-time collaboration, direct on-demand tunnels with decentralized policy enforcement on each spoke ion device are preferred. For sensitive data transfers that must be inspected by a centralized firewall, for example, financial data moving between a branch office and a regional finance center, hub routing through a site with a Palo Alto Network's next-generation firewall or Prisma Access provides the required security inspection. The network policy on each spoke controls this choice through the service endpoint definition for branch-to-branch traffic flows. The security policy on each spoke ion must explicitly permit traffic from the sdwan overlay zone representing the incoming on-demand tunnel traffic from other branches to the corporate LAN zone. This is one of the two most commonly missed policy configurations in new deployments, as we discussed in the previous section. Without this rule, all inbound spoke-to-spoke traffic is silently denied by the implicit deny all rule at the bottom of the security policy stack. Application Quality of Experience Monitoring and Adaptive Policy. Application Quality of Experience Monitoring, commonly abbreviated QoE, is the mechanism by which Prisma sdwan measures not just network-level path quality metrics, but actual end-to-end application performance as experienced by users. QoE monitoring closes the gap between network health, which tells you about link quality, and application health, which tells you whether users are actually getting good performance from their applications. This distinction is important and often comes up in interviews focused on operations and user experience. Traditional network monitoring measures path metrics at the network layer. Latency between two IP addresses, packet loss on a WAN interface, jitter on a circuit. These metrics are necessary but not sufficient for understanding user experience. A path might show excellent network metrics, 20 millisecond latency, 0 packet loss, while a specific application is performing poorly because of a server-side issue, a DNS resolution problem, or application layer protocol inefficiency. Network metrics alone would not identify this problem. Prisma sdwan QoE monitoring works at the application flow level. For each active application session, the ION device measures the complete round-trip transaction time from when the client sends a request to when the server's response is fully received. For HTTP and HTTPS traffic, this corresponds to the time from the HTTP request being sent to the last byte of the HTTP response being received. For voice and video, it corresponds to the MOS score, mean opinion score, calculated from the measured packet loss, latency, and jitter using the eModel algorithm defined in ITUTG.107. The MOS score maps network metrics to a perceptual quality score on a scale from 1 to 5, where scores above 4 indicate excellent quality, scores between 3 and 4 indicate acceptable quality, and scores below 3 indicate poor quality that users will actively complain about. The adaptive policy capability in Prisma sdwan allows quality of experience scores to trigger automatic policy adaptations. When the measured MOS score for voice traffic on a specific WAN path drops below the configured threshold, for example, below 3.5, the ION device can automatically activate FEC on that path, migrate the affected flows to a better performing path, or generate an alarm for the operations team. This policy adaptation happens in real time without human intervention, ensuring that voice quality degradation is addressed within seconds of being detected rather than waiting for a user complaint to reach the help desk. Hybrid WAN policy, MPLS, broadband, and LTE together. Hybrid WAN policy design where MPLS, broadband internet, and LTE cellular backup are all active simultaneously on a single ION device represents the most common production deployment scenario for enterprise SD-WAN. Getting the policy design right for a hybrid WAN requires understanding how each transport type's characteristics should influence the policy rules, and how the ION device should behave when transports fail or degrade in various combinations. The starting point for hybrid WAN policy design is accurately characterizing each transport type's performance profile. MPLS circuits provide predictable, low latency, low jitter connectivity with guaranteed bandwidth from the carrier. They are the most expensive transport but provide the highest quality and reliability for business-critical traffic. Broadband internet connections, fiber, cable, or DSL provide high bandwidth at low cost but with variable performance. Latency and jitter on broadband links fluctuate based on carrier congestion, time of day, and shared neighborhood bandwidth usage. They are suitable for standard business traffic and as fallback paths for critical traffic. LTE and 5G cellular provide wireless backup connectivity that is independent of the fixed line infrastructure if the building's MPLS and broadband circuits both fail due to a physical cut to the building. The LTE circuit continues to function. LTE is the most expensive per megabyte transport and typically has the highest latency of the three options. A well-designed hybrid WAN policy stack typically has 5 layers of rules. The first layer handles real-time UC traffic steered exclusively to MPLS with LTE fallback but no broadband fallback, because broadband jitter makes it unsuitable for voice even though its latency may be acceptable. The second layer handles business-critical software as a service and ERP traffic steered to MPLS with broadband fallback. No LTE fallback unless both MPLS and broadband are unavailable. The third layer handles direct internet breakout for trusted software as a service steered to broadband for performance and cost efficiency, with LTE fallback. The fourth layer handles all other internet traffic steered to broadband through Prisma Access, with LTE fallback only for essential connectivity. The fifth layer is the catch-all default. Any unclassified traffic uses broadband and falls back to LTE. The LTE circuit should almost never be the preferred path for any application category. It should always be a last resort fallback. This is both a performance consideration and a cost consideration. LTE data is expensive, and in many enterprise contracts, LTE circuits have data caps. Routing significant volumes of traffic over LTE unnecessarily will result in high carrier bills and potential throttling when the data cap is reached. The policy design should be explicit about which traffic categories are permitted to use LTE as a fallback and which must wait for a fixed line circuit to recover before resuming transmission. Threat prevention profiles in security policy. Threat prevention profiles are security objects attached to security policy permit rules that instruct the ion device or prisma access to actively inspect permitted traffic for malicious content, rather than simply forwarding it because it matched a permit rule. Understanding how to configure and apply threat prevention profiles is an important topic for any security-focused Prisma sdwan interview, particularly for candidates targeting SASE architect or security engineer roles. A security policy permit rule without a threat prevention profile is what security professionals call a stateful permit. It verifies that the traffic matches the defined criteria and is part of a valid session, but it does not inspect the content of the traffic for threats. This is analogous to a border guard who checks your passport and visa but does not search your luggage. A permit rule with a threat prevention profile attached adds content inspection. The guard checks your passport and searches your luggage for prohibited items. Prisma sdwan supports 4 categories of threat prevention profiles that can be attached to security policy rules. The first is IPS, Intrusion Prevention System, profiles, which contain signatures for known attack patterns, exploitation techniques, and network scanning behaviors. When the IPS engine detects a packet that matches an attack signature, it can either generate an alarm, in detection mode, or drop the packet and reset the connection, in prevention mode. Production security policies should always run IPS in prevention mode for known, high-confidence threats. The second category is antivirus profiles, which scan file transfers, HTTP downloads, FTP transfers, email attachments for known malware signatures. The antivirus engine maintains a continuously updated database of malware file hashes and behavioral patterns. Files that match known malware are blocked and the transfer is terminated. The third category is anti-spyware profiles, which detect and block command and control traffic, the network communications that malware uses to receive instructions from attacker infrastructure and exfiltrate stolen data. Anti-spyware is one of the most valuable threat prevention capabilities because it can detect an already compromised endpoint attempting to communicate with an attacker even when the initial infection bypassed other controls. The fourth category is vulnerability protection profiles, which target exploitation of software vulnerabilities, buffer overflows, SQL injection in application traffic, exploitation of protocol weaknesses. Together, these 4 profile types form a comprehensive defense in-depth framework that should be applied to all interzone and internet-bound traffic in a production Prisma sdwan deployment. Large-scale policy deployment best practices. Large-scale policy deployment, managing policies across hundreds or thousands of branch sites, introduces operational challenges that do not appear in smaller deployments. The best practices for large-scale Prisma sdwan policy management are a topic that signals genuine enterprise deployment experience to an interviewer, because they reflect hard-won lessons from real production environments. The first best practice is to design for policy set reuse from the beginning. Every organization has a temptation to customize policies for individual sites. This branch needs a special rule because of this specific application. Resist this temptation strongly. Every site-specific policy exception creates a divergence from the standard policy set that must be maintained, tested, and updated independently. Across 500 sites, even a small number of site-specific exceptions creates an unmanageable long tail of policy variations. Instead, design policy sets to accommodate the range of requirements through application groups, prefix filters, and SLA profile variations within a standardized framework. The goal is to have no more than 3 or 4 policy set variants: standard branch, large campus, IoT site, and cloud site, regardless of how many sites the deployment includes. The second best practice is to stage policy changes through a deployment ring model. Rather than pushing a policy change directly to all sites simultaneously, define 3 deployment rings. Ring 0 contains 1 or 2 lab or canary sites where changes are validated first. Ring 1 contains a representative sample of 10 to 20 production sites across different regions and site types. And Ring 2 contains all remaining production sites. Every policy change is deployed to Ring 0 and monitored for 24 hours. Then deployed to Ring 1 and monitored for 48 hours. And only then deployed to Ring 2. This staged approach means that a defective policy change affects at most 1 or 2 sites before it is identified and rolled back, rather than simultaneously disrupting the entire network. The rollout stages can be automated through the REST API by assigning sites to ring groups and building the staged deployment into the CI/CD pipeline. The third best practice is to maintain a policy object naming convention that encodes the object's purpose, owner, and creation date. For example, a prefix filter created for the finance department's server subnets in March 2024 should be named something like Finance Servers DC1 2024 Q1 rather than just Finance Servers. The structured name makes it immediately clear in the portal who owns the object and when it was last reviewed. When you are auditing a policy with hundreds of objects and rules, descriptive, structured naming is the difference between a manageable audit and an impenetrable maze of cryptic rule names that no one remembers the purpose of. Policy configuration. Complete interview cheat sheet. This final slide brings together the complete policy knowledge from all 3 decks into a single cheat sheet organized by the most important interview topics. Use this as your final review before any Prisma sdwan interview. Let me walk through each section and highlight the single most important point in each area. For the policy evaluation order, the single most important thing to remember is the complete 8-step sequence: zone identification, session lookup, DPI classification, security policy, application policy, network policy, QoS assignment, NAT translation. If you can recite this sequence in order without hesitation, you have demonstrated expert knowledge of how the ION device processes every flow. For network policy, the single most important concept is that path groups use WAN interface labels to abstract physical interfaces, making policies transport agnostic and portable across all site types. Never write a network policy rule that references a specific interface name, always reference a path group. For application policy, the single most important concept is that SLA profiles drive proactive path migration, not just reactive failover. The ION device migrates flows when the path degrades below the SLA threshold, not when the link completely fails. This is what makes the platform proactive rather than reactive. For security policy, the 2 things that break branch connectivity most often are a missing permit rule from the corporate LAN zone to the SD-WAN overlay zone blocking all branch-to-branch and branch-to-data center traffic, and the implicit deny all at the bottom of every policy stack, silently dropping traffic that does not match any permit rule. Always verify both of these when troubleshooting connectivity failures. For network address translation policy, the single most important rule is that network address translation exemption must always be Rule 1. Placed above the source NAT rule. If SNAT fires on overlay traffic, private addressed traffic gets natted and the return path breaks silently. For quality of service policy, always size the real-time queue guarantee based on the maximum number of concurrent voice and video calls, not average usage. Undersizing Q0 means call quality degrades exactly when the network is busiest, which is precisely when reliable voice communication is most critical. Thank you for your attendance. Please consider subscribing to the channel and liking this